The James Webb Telescope has spotted a galaxy so far away that it raises troubling questions about the very dawn of our universe. This smudge of light, known technically as JADES, GSZ14-0, but which we will call the dawn, should not exist where we found it. It is too bright, too large, and far too mature for a time when the cosmos was supposed to be in its infancy. If our current models of physics are correct, the first stars should not have had enough time to gather in such massive numbers. Yet there it sits, glowing defiantly from a time just 290 million years after the Big Bang. We are looking at a ghost from the beginning of time that is forcing us to ask, is our history of the universe fundamentally wrong? To appreciate why the dawn is so troubling, we need to understand what astronomers expected to find at that distance and why the reality was so different. Because the story of this galaxy is not just a story about one smudge of light in a telescope image. It is a story about the foundation of everything we thought we knew about how the universe works. And that foundation is showing cracks. The James Webb Space Telescope is the most powerful observatory ever placed in space. It sits roughly 1.5 million kilometers from Earth at a gravitationally stable point called the second Lagrange point, far enough from our planet to avoid the heat and light that would interfere with its incredibly sensitive instruments. Its primary mirror is 6.5 meters across, made of 18 hexagonal segments of gold-coated beryllium that unfold in space like the petals of a mechanical flower. This mirror collects infrared light, the kind of light that is invisible to human eyes, but that carries information from the most distant and most ancient objects in the universe. The reason Webb needs to see infrared light is rooted in one of the most important principles in all of cosmology. As light travels across the expanding universe, its wavelength gets stretched. Imagine drawing a wave on a rubber band and then pulling the rubber band from both ends. The peaks of the wave move further apart. The wavelength gets longer. Light works exactly the same way. A photon that was emitted billions of years ago as visible blue or ultraviolet light has been stretched during its journey across the expanding cosmos until it arrives at our telescopes as infrared light. The further the object, the more the light has been stretched, and the deeper into the infrared it has shifted. This stretching of light is called redshift. It is one of the most powerful tools in astronomy because the amount of stretching tells you how far away the object is and how long ago the light was emitted. A redshift of 1 means the light has been stretched by a factor of 2. A redshift of 5 means it has been stretched by a factor of 6. The dawn has a redshift of roughly 14.18. That means its light has been stretched by a factor of more than 15. Light that was originally emitted in the ultraviolet by young hot stars has been stretched so far into the infrared that no telescope operating in visible light could ever detect it. Only Webb, with its infrared eyes, could see this ancient phantom. A redshift of 14.18 corresponds to a time approximately 290 million years after the Big Bang. Let that number settle for a moment. The universe is 13.8 billion years old. The dawn existed when the universe was barely 2% of its current age. If the entire history of the cosmos were compressed into a single year, with the Big Bang at midnight on January 1st, and the present day at midnight on December 31st, the dawn would appear on January 8th. We are looking at something that existed in the first week of cosmic history, and it should not look the way it does. When astronomers first detected the dawn in data from the JADES survey, which stands for the James Webb Space Telescope Advanced Deep Extragalactic Survey, they were cautious. JADES is one of the most ambitious observing programs in the history of astronomy. It uses hundreds of hours of Webb time to study a small patch of sky near the Hubble Ultra-Deep Field, a region that has been observed repeatedly by multiple telescopes over the past 2 decades. The choice of this region was deliberate. It is one of the best studied areas of the sky, and observations at multiple wavelengths provide a rich context for interpreting new discoveries. The JADES program is a collaboration between 2 of the instrument teams that built Webb's primary science instruments, the Near-Infrared Camera team and the Near-Infrared Spectrograph team. Together, these teams have access to guaranteed observing time that was allocated in exchange for building the instruments. This guaranteed time has been used to conduct some of the deepest surveys ever attempted, pushing the telescope to its limits of sensitivity. The initial identification of the dawn came from imaging data obtained with Webb's near-infrared camera in October 2023 during a 5-day deep imaging campaign that formed what the team called the JADES Origins Field. The galaxy appeared as a faint reddish smudge close to a foreground galaxy, which initially made it difficult to determine whether the 2 objects were neighbors or separated by billions of light years. But the filters used in the deep imaging were specifically designed to isolate extremely distant galaxies, and the data grew increasingly convincing. In January 2024, the team aimed Webb's near-infrared spectrograph at the dawn for nearly 10 hours. A spectrograph splits light into its component wavelengths, the way a prism splits white light into a rainbow. Different elements absorb and emit light at specific wavelengths, creating a unique chemical fingerprint. By reading that fingerprint, astronomers can determine what an object is made of, how fast it is moving, and how far away it is. When the spectrum of the dawn was processed, the result was unambiguous. The galaxy was at a redshift of approximately 14.32, shattering the previous distance record held by another galaxy in the same survey. Later refinements using data from the ALMA radio telescope in Chile narrowed the redshift to 14.796, one of the most precise distance measurements ever made for an object this far away. The precision was extraordinary, equivalent to being accurate within 5 centimeters over a distance of 1 kilometer. But it was not the distance that stunned the team. It was what the galaxy looked like at that distance. The dawn is over 1,600 light years across. That might sound small compared to the Milky Way, which spans roughly 1,000,000 light years. But for a galaxy that existed just 290 million years after the Big Bang, it is enormous. The standard models of galaxy formation predict that the first galaxies should have been small, dim, and chaotic. Tiny clumps of gas barely held together by gravity, producing a sputtering of faint stars in the darkness. The dawn is none of those things. It is bright, it is structured, and its light is produced overwhelmingly by young stars, not by gas falling into a black hole. The mass of the galaxy is estimated at several 100 million times the mass of our Sun, a staggering amount of stellar material to have assembled in less than 300 million years. The brightness of the dawn was the first troubling question. The galaxy is one of the most luminous objects ever observed at such an extreme distance. In the standard picture of cosmic evolution, the earliest galaxies should be faint, requiring the most powerful telescopes and the longest exposure times to detect. The dawn is not faint. It practically announced itself in the data. And its brightness is not coming from an active black hole at the center, gobbling matter and blasting out radiation. The large physical size of the galaxy rules that out. The light is stellar. It is the combined glow of an enormous population of young, hot stars burning through their hydrogen fuel. But where did all those stars come from? How did they form so quickly? And how did they gather together into a structure this large in what amounts to the blink of a cosmic eye. The color of the dawn added another layer of mystery. Astronomers expected that the earliest galaxies would appear blue, the signature of very young, very hot stars formed from pristine hydrogen and helium gas. The dawn is not as blue as it should be. Its light shows signs of being reddened by dust. Dust in astronomy refers to tiny solid particles made of silicates, carbon compounds, and other materials that are produced inside stars and released into space when those stars explode. The presence of dust in a galaxy tells you that stars have already formed, lived their lives, and died, scattering their processed material into the surrounding gas. Finding significant dust in a galaxy that is only 290 million years old means that the cycle of stellar birth and death had already been running for some time before we see it. The dawn is not showing us the beginning of star formation. It is showing us a process that was already well underway. And then came the discovery that truly shook the astronomical community. In March 2025, two independent teams of astronomers pointed the ALMA telescope in Chile at the dawn. ALMA observes at millimeter and sub-millimeter wavelengths much longer than the infrared light that Webb detects. These wavelengths can reveal the presence of specific atoms and molecules in distant galaxies through their characteristic emission lines. Both teams detected something that should not have been there. Oxygen. Not just a trace of oxygen, a significant amount. The two studies indicated that the dawn contains roughly 10 times more heavy elements than models predicted for a galaxy at this distance. The gas phase metallicity, which is the astronomers' way of measuring the abundance of elements heavier than hydrogen and helium, was found to be greater than 10% of the Sun's metallicity. For a galaxy that existed when the universe was only 2% of its current age, this level of chemical enrichment is astonishing. One of the lead researchers described the finding by comparing it to discovering an adolescent, where you would only expect to find babies. The evidence suggested that the galaxy had formed and matured far more rapidly than any model had predicted, adding to the growing body of evidence that galaxy formation in the early universe happened much faster than expected. The oxygen discovery matters because oxygen is not a primordial element. The Big Bang produced only hydrogen, helium, and tiny traces of lithium. Every atom of oxygen in the universe was forged inside a star through the process of nuclear fusion and then scattered into space when that star died, either through stellar winds or the catastrophic explosion of a supernova. For oxygen to be present in the dawn at the levels observed, a complete generation of massive stars had to have been born, lived their brief violent lives, and died in supernova explosions before the galaxy we are seeing even reach the state we observe. The oxygen did not appear overnight. It required an entire cycle of stellar evolution to produce. Think about what that means for the timeline. We are seeing the dawn at 290 million years after the Big Bang. But for this galaxy to contain this much oxygen, star formation must have begun significantly earlier, perhaps 100 million years or more, before we observe it. That pushes the onset of star formation back to roughly 200 million years after the Big Bang, or even earlier. The first stars in this galaxy may have ignited when the universe was barely 1% of its current age. This is much earlier than most models had predicted, and it raises a deeply troubling question. How did the conditions for star formation come together so quickly after the Big Bang? What mechanism allowed gravity to gather enough gas, compress it to sufficient density, and trigger nuclear fusion in such a phenomenally short period of time? The oxygen detection also allowed the astronomers to refine the distance measurement with remarkable precision. The redshift derived from the oxygen emission line 14.11796 is consistent with a tentative detection of carbon that had been made earlier using Webb's spectrograph. Carbon, like oxygen, is produced inside stars, and its presence at this distance tells the same story. Multiple generations of stars lived and died in the dawn before we ever saw it. The chemistry of this galaxy is not primitive. It is surprisingly mature, and that maturity is one of the strongest pieces of evidence that something about our understanding of the early universe needs to change. There is another detail about the dawn that deserves attention before we move on. The galaxy appears to have a surprisingly low gas fraction. When astronomers modeled the mass budget of the dawn using combined data from Webb and ALMA, they found that the total dynamical mass, the mass inferred from the motion of gas within the galaxy, suggests that a large portion of the original gas has already been converted into stars or expelled from the galaxy entirely. Some models suggest that powerful outflows driven by the intense burst of star formation may have swept gas and dust out of the galaxy, carving channels through the surrounding material and allowing ultraviolet radiation to escape into the intergalactic medium. This idea is supported by the detection of a thick column of neutral hydrogen gas in front of the dawn, seen as a damped absorption feature in the spectrum. This cloud of hydrogen sits in front of the galaxy and absorbs some of its light. Some researchers believe this cloud could be the remnant of a galactic outflow material that was once inside the dawn, but was ejected by the ferocious energy of the starburst. If this interpretation is correct, it means the dawn was not just forming stars at an extraordinary rate, it was also expelling material at an extraordinary rate. The galaxy was simultaneously building itself up and tearing itself apart. The combination of high stellar mass, high metallicity, significant dust, possible outflows, and low gas fraction paints a picture of a galaxy that has already been through a turbulent and eventful life, despite being observed when the universe was barely 300 million years old. It is not the quiet, primitive proto-galaxy that the models predicted. It is a mature, dynamic, and complex system that has undergone rapid evolution in a fraction of the time that our models say should be required. And the dawn is not alone. It has a companion. Detected in the same survey and at nearly the same distance, a galaxy designated as its sibling exists at a redshift of approximately 13.86, corresponding to a time only slightly later in cosmic history. But this companion is strikingly different. It is much smaller, much fainter, and much more compact, with a physical size of less than 50 light years. Its spectrum shows no strong metal emission lines, suggesting a much lower level of chemical enrichment. This contrast is itself a mystery. How can two galaxies existing at virtually the same moment in cosmic history be so different in their properties? One is bright, massive, and chemically mature. The other is faint, tiny, and chemically primitive. The early universe apparently contained an enormous diversity of galaxies, even within its first few 100 million years. The companion galaxy received an extraordinary amount of observing time, roughly 70 hours of mid-infrared imaging from Webb's MIRI instrument, the deepest MIRI exposure ever obtained for any high redshift galaxy. Despite this unprecedented depth, the detection of the companion at mid-infrared wavelengths was only tentative at roughly 3 times the noise level. This faintness in the mid-infrared suggests that the companion has much weaker emission lines from oxygen and hydrogen than the dawn, consistent with a lower metallicity and a less active star formation history. The contrast between the two galaxies, separated by only a modest difference in redshift, but vastly different in their properties, illustrates the remarkable variety of conditions that existed in the early universe. The companion is unresolved in all 16 near-infrared camera bands, meaning it is consistent with a point source or an extremely compact object smaller than 50 parsecs across. This compactness makes it one of the smallest spectroscopically confirmed galaxies at any redshift. Its stellar mass is estimated at roughly 40 million solar masses, with a star formation rate of about 2 solar masses per year. The absence of strong metal emission lines despite this active star formation rate suggests either a very low gas phase metallicity below 10% of the Sun's value, or a high escape fraction of ionizing photons that are leaving the galaxy rather than exciting the surrounding gas to produce emission lines. The existence of this companion raises fascinating questions about the environments in which the first galaxies formed. Were the dawn and its companion born from the same primordial gas cloud, or did they form independently in nearby but separate dark matter halos? Did one influence the formation of the other through gravitational interactions, or through the radiation and outflows from its star formation? And will they eventually merge, combining their stellar populations and gas reservoirs into a single, larger galaxy? At the distances involved, resolving these questions observationally is extremely challenging, but future deeper observations may provide clues. Now let us step back and examine the framework that the dawn is challenging, because the significance of this discovery can only be understood in the context of the model it contradicts. And that model, the Standard Model of Cosmology, has been one of the most successful scientific theories in history. The Standard Model of Cosmology is known as Lambda Cold Dark Matter, or Lambda CDM for short. Lambda represents dark energy, the mysterious force that is driving the accelerating expansion of the universe. CDM stands for cold dark matter, the invisible matter that provides the gravitational scaffolding on which galaxies and galaxy clusters are built. Together, these two components, along with ordinary matter radiation and the initial conditions set by the Big Bang, define a mathematical framework that describes how the universe has evolved over the past 13.8 billion years. Lambda CDM has been spectacularly successful. It correctly predicts the detailed pattern of temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang that fills every direction of the sky. It explains the observed distribution of galaxies and galaxy clusters on the largest scales. It accounts for the abundances of hydrogen, helium, and lithium produced in the first few minutes after the Big Bang. And it provides a framework for understanding how the universe expanded from a hot, dense state to the vast, cold cosmos we observe today. One of the central predictions of Lambda CDM is that structure in the universe forms hierarchically. Small structures form first and then merge over time to create larger ones. In the context of the galaxies, this means that the first galaxies should have been small, roughly a few thousand to a few million times the mass of the Sun. These proto-galaxies then merged with each other over billions of years, gradually building up the massive galaxies we see in the local universe. The Milky Way itself is thought to be the product of dozens or even hundreds of such mergers over cosmic history. This hierarchical merging model makes a very specific prediction about the early universe. At 290 million years after the Big Bang, the structures that would eventually become galaxies should still be in their infancy. The dark matter halos the invisible gravitational scaffolding that holds galaxies together should be relatively small. The amount of gas that has collapsed into these halos should be modest, and the rate of star formation should be limited by the amount of available gas and the efficiency with which that gas can cool collapse and ignite nuclear fusion. The dawn violates these predictions in almost every way. Its mass is too high, its metallicity is too advanced, its dust content is too significant, its luminosity is too great, and the implied rate of star formation required to build it in the available time pushes the boundaries of what our models say is physically possible. If lambda CDM is correct, then something extraordinary must have happened in the region where the dawn formed. The local conditions must have been uniquely favorable for rapid galaxy growth, producing an extreme outlier in the general population of early galaxies. But here is the problem. The dawn is not the only galaxy like this. The JADES survey, despite covering only a small patch of sky, has already found multiple galaxies at extreme redshifts that are brighter and more massive than the models predict. If the dawn were a 1 in a billion statistical fluke, that would be one thing. But finding several such galaxies in a small survey area implies that they are not flukes at all. They are part of a population that the standard model did not predict and cannot easily explain. The discovery team noted this explicitly. They wrote that the discovery of the dawn in such a small region of sky has profound implications for the predicted number of bright galaxies in the early universe. The number density of luminous galaxies at this epoch appears to be more than 10 times higher than what was expected based on observations made before Webb launched. This is not a minor discrepancy. It is an order of magnitude disagreement between observation and prediction. Something in our models is wrong. The question is what? There are several possible explanations, and each one, if correct, would have different implications for our understanding of the cosmos. The first and most conservative explanation is that star formation in the early universe was simply more efficient than we assumed. Our models of star formation are calibrated primarily against observations of nearby galaxies in the present-day universe. In those galaxies, only a fraction of available gas, typically 10 to 30%, is converted into stars during any given episode of star formation. The rest is either too warm, too turbulent, or too diffuse to collapse. But the conditions in the early universe were different. The first gas clouds were made of pure hydrogen and helium with no heavy elements and no dust. The physics of how this pristine gas collapses and forms stars is not identical to how metal-enriched gas behaves in modern galaxies. Some theoretical models suggest that the absence of heavy elements could actually lead to more efficient cooling under certain conditions, particularly in the presence of strong radiation fields that can dissociate molecular hydrogen and alter the thermal properties of the gas. If the first episodes of star formation converted a larger fraction of the available gas into stars, 50% or even higher, then galaxies could have built up stellar mass much faster than the standard models predict. This explanation preserves the basic framework of lambda CDM while adjusting a specific parameter, but it has limits. Even with maximally efficient star formation, there is still a physical constraint on how quickly gas can accumulate and collapse. The gas has to fall into the dark matter halo. It has to cool. It has to fragment. And then nuclear fusion has to ignite. Each of these steps takes time. Pushing the star formation efficiency to extreme values helps, but it may not be enough to fully explain the most massive early galaxies. The second explanation goes deeper. What if the problem is not with star formation, but with dark matter itself? The cold dark matter model predicts a specific rate at which dark matter halos grow through merging in the early universe. If dark matter has properties that allow it to clump more effectively than the standard model predicts, then halos could grow larger faster and provide a bigger gravitational well for gas to fall into. This would give the first galaxies a head start on star formation and could help explain their unexpectedly rapid growth. Some theorists have proposed models where dark matter particles interact with each other through forces beyond gravity, allowing them to exchange energy and momentum in ways that affect halo formation. Others have suggested that dark matter might not be a single type of particle, but a family of particles with different properties. These alternative dark matter models are speculative, but they are being taken increasingly seriously because the standard cold dark matter model is struggling to explain the growing body of evidence from James Webb. A third and more radical explanation involves challenging the expansion history of the universe itself. The age we assign to the dawn, 290 million years after the Big Bang, is not a directly measured quantity. It is calculated from the redshift using the lambda CDM model, which defines how the universe has expanded over time. If the expansion history is different from what lambda CDM predicts, then the same redshift could correspond to a different cosmic age. The galaxy might be older than 290 million years at the time. We are seeing it giving it more time to form and evolve. This would require changes to fundamental parameters of the cosmological model, changes that would need to be consistent with all other observations, including the cosmic microwave background and the distribution of galaxies at lower redshifts. The tension between observations and models has been building for years, even before the dawn was discovered. One of the most persistent anomalies in cosmology is the Hubble tension, the disagreement between two independent methods of measuring the expansion rate of the universe. Measurements based on the cosmic microwave background give a lower expansion rate than measurements based on nearby supernovae and pulsating stars. The discrepancy is not large in absolute terms, roughly 67 versus 73 kilometers per second per megaparsec, but it is statistically significant. The measurements are precise enough that the probability of the disagreement being due to random error is vanishingly small. Something real is causing the discrepancy. Either one or both measurement methods have an unidentified systematic error, or there is physics in the real universe that our models do not capture. The Hubble tension matters for the early galaxy problem because the expansion rate is directly connected to the age of the universe. A higher expansion rate implies a younger universe. If the universe is younger than 13.8 billion years, then the time available for structure formation at any given redshift is shorter, making the existence of massive early galaxies even harder to explain. Conversely, if there is unknown physics that causes the expansion rate to vary in ways that our model does not account for, then the relationship between redshift and age might be different from what we calculate. Galaxies at redshift 14 might not correspond to 290 million years after the Big Bang. They might correspond to a slightly different age depending on the details of the expansion history. If the higher value is correct, it could mean the universe is expanding faster than lambda CDM predicts, which would affect the relationship between redshift and cosmic age for all distant objects. James Webb has contributed to this debate as well. Early observations from Webb have been used to recalibrate parts of the cosmic distance ladder, the chain of measurements that links nearby distance indicators to more distant ones. Some of these recalibrations support the higher expansion rate. If confirmed, this would mean the universe is slightly younger than the lambda CDM estimate of 13.8 billion years. And a younger universe would make the early galaxy problem even worse because there would be even less time for structures to form. But there is also a possibility that goes in the opposite direction. Some theorists have proposed models where the expansion rate varies in ways that lambda CDM does not capture. If dark energy, the force driving the acceleration of the expansion, is not a constant but changes over time, then the expansion history could be significantly different from the standard prediction. In some of these models, the universe could be slightly older than 13.8 billion years, providing more time for early galaxy formation. The challenge is to find a model that simultaneously explains the cosmic microwave background, the Hubble tension, and the early galaxy observations without creating new contradictions with other data. Let us return to the oxygen and explore what it truly means in the context of cosmic evolution. Because the detection of oxygen in the dawn is not just a chemical curiosity, it is a clock that tells us something profound about what happened before the galaxy we are seeing was even assembled. Oxygen is the third most abundant element in the universe today, after hydrogen and helium. But unlike hydrogen and helium, which were created in the Big Bang, every atom of oxygen in the cosmos was manufactured inside a star. Specifically, oxygen is produced in the cores of massive stars through a chain of nuclear fusion reactions that begins with hydrogen progresses through helium and carbon, and eventually reaches oxygen. These massive stars are the factories of the periodic table. They take the simple ingredients left over from the Big Bang and forge them into the complex elements that will eventually form planets, oceans, atmospheres, and living things. But the oxygen does not stay inside the star. When a massive star exhausts its fuel, it collapses and explodes as a supernova, scattering its processed material into the surrounding gas. This enriched gas then mixes with the pristine hydrogen and helium in the interstellar medium. Over time, new stars form from this enriched gas, incorporating the heavy elements into their structure. The process repeats, with each generation of stars producing more heavy elements and enriching the galaxy further. Astronomers call this process chemical evolution, and it is one of the primary ways that galaxies change over time. The amount of oxygen in a galaxy tells you something important about its history. A galaxy with very little oxygen has not yet had many generations of stars. Its stellar population is young, and its gas is still mostly pristine. A galaxy with a lot of oxygen has been through multiple cycles of star formation and death. Its stellar population includes both young stars and the processed remnants of older ones. Its gas has been enriched by supernovae over a long period of time. The dawn has a gas phase metallicity greater than 10% of the Sun's metallicity. This might not sound like a lot, but in the context of a galaxy that is only 290 million years old, it is extraordinary. To reach this level of enrichment requires multiple complete cycles of stellar evolution. Massive stars have to form, burn through their fuel, in a few million years explode as supernovae scatter their heavy elements into the surrounding gas, and then new stars have to form from that enriched gas. Each cycle takes time. Even for the most massive and short-lived stars, a single cycle of formation, evolution, and death takes several million years. Multiple cycles require tens of millions of years at minimum. Working backward from the observed metallicity, researchers estimate that star formation in the dawn must have been underway for at least 100 million years before we observe it. That pushes the beginning of star formation in this galaxy back to roughly 200 million years after the Big Bang, and possibly earlier. At that time, the universe was emerging from the cosmic dark ages, the period after the cosmic microwave background was released, when no stars existed and the universe was filled with nothing but cold, dark, neutral hydrogen gas. The Dark Ages are one of the most mysterious chapters in cosmic history. After the universe became transparent roughly 30,000 years after the Big Bang, the light from that era, the cosmic microwave background, was released and began streaming through space. But there was nothing to produce new light. The universe was dark, No stars, no galaxies, no sources of illumination at all. Just an endless expanse of cold neutral hydrogen, slowly being gathered together by the patient pull of gravity. To appreciate the darkness of this era, consider that the only radiation present was the fading afterglow of the Big Bang itself, the cosmic microwave background. At 38,000 years after the Big Bang, this radiation was the temperature of the surface of a red giant star, roughly 3,000 Kelvin, glowing a deep reddish orange. But as the universe expanded, the radiation cooled. By the time the first stars would ignite hundreds of millions of years later, the background radiation had cooled to roughly 60 Kelvin, nearly 50 degrees below the freezing point of water on the absolute scale. The universe was not just dark, it was cold. Colder than the surface of Pluto, colder than the vacuum between the stars in the modern Milky Way. The only warmth was hidden deep inside the densest clumps of collapsing gas, where the pressure of gravitational compression was beginning to raise temperatures toward the ignition point of nuclear fusion. During this cold, dark epoch, the hydrogen gas that filled the universe was slowly responding to gravity. Everywhere the gas was perfectly uniform, nothing happened. But the universe was not perfectly uniform. The quantum fluctuations of the inflation epoch had been stretched to cosmic scales, creating a landscape of subtle density variations across the universe. Where the density was slightly above average, the gravitational pull was slightly stronger, attracting more gas from the surrounding regions. These overdense regions grew slowly, imperceptibly at first, then with increasing speed, as the accumulating mass strengthened the gravitational pull further. Dark matter was the dominant player in this process. For every kilogram of ordinary matter in the universe, there are roughly 5 kilograms of dark matter. Dark matter does not interact with light, and it does not experience the pressure forces that prevent ordinary matter from collapsing too quickly. It simply responds to gravity. And so dark matter collapsed first, forming a network of dense structures called halos that served as the gravitational scaffolding for everything that followed. Ordinary matter, the hydrogen and helium that would eventually become stars, fell into these dark matter halos and began to accumulate. The process was slow at first. The density contrasts were small and the gravitational forces were weak. But gravity is patient and relentless. Over tens of millions of years, the halos grew, the gas accumulated, and the densities increased. Eventually, in the most massive halos, the gas at the center became dense enough and hot enough for nuclear fusion to begin. A hydrogen atom was squeezed against another hydrogen atom, hard enough for the nuclear force to fuse them together, releasing energy. The first star in the history of the universe ignited, and the Dark Ages ended. Gravity worked on the tiny density fluctuations that were seeded during inflation, the period of exponential expansion in the first fraction of a second after the Big Bang, where the gas was slightly denser than average gravity, pulled more gas toward it. Over tens of millions of years, these subtle density differences grew into larger concentrations of gas that eventually became dense enough for nuclear fusion to begin. The first stars ignited, ending the Dark Ages with a flood of ultraviolet light that began to ionize the surrounding neutral hydrogen. The standard models predict that this transition from darkness to first light happened roughly 100 to 200 million years after the Big Bang. The first stars were thought to be population 3 stars, massive giants formed from pristine hydrogen and helium with no heavy elements. These stars would have been enormous, perhaps hundreds of times the mass of the Sun, and they would have burned through their fuel quickly, living only a few million years before exploding as supernovae, and seeding the surrounding gas with the first heavy elements. Population 3 stars occupy a unique place in theoretical astrophysics. They are the only generation of stars for which we have no direct observational evidence. Every star ever observed, every stellar spectrum ever recorded, every galaxy ever studied contains stars that have at least some heavy elements in their composition. Population 3 stars, by definition, formed from gas that contain none. Their properties can only be inferred from theoretical models and simulations which predict that the absence of heavy elements would have produced stars that were qualitatively different from anything in the modern universe. Without heavy elements, the gas from which population 3 stars formed could not cool as efficiently as modern interstellar gas. In today's universe, heavy elements and dust grains act as coolants, radiating away the heat generated by gravitational compression and allowing the gas to fragment into small, dense clumps that become individual stars. In the pristine gas of the early universe, the primary coolant was molecular hydrogen, which is a much less efficient radiator. Without efficient cooling, the gas clouds could not fragment into small pieces. They collapsed as massive units, producing stars that were extraordinarily large by modern standards. Some simulations predict that population 3 stars could have reached masses of 300, 500, or even 1,000 times the mass of the Sun. Such stars would have been fantastically luminous, outshining our Sun by millions of times. They would have emitted fierce torrents of ultraviolet radiation, ionizing the gas around them for distances of millions of light years. And they would have been short-lived, exhausting their nuclear fuel in just 2 to 3 million years before collapsing in supernovae of unprecedented power. The supernovae of population 3 stars would have been the most energetic stellar explosions in the history of the cosmos. Some of these stars may have ended their lives as pair instability supernovae, a type of explosion where the nuclear reactions in the core produce so much energy that the entire star is disrupted, leaving no remnant behind. Others may have collapsed directly into black holes potentially, with masses of hundreds of solar masses, providing the first seeds for the growth of supermassive black holes. But the oxygen in the dawn suggests that this process happened even faster than the standard models predict. Not only did the first stars form early, they formed, lived, died, enriched their environment, and then a second generation of stars formed from the enriched gas, all within the first 200 million years. And these second generation stars then lived, died, and enriched the environment further, producing the levels of oxygen that we observe. The chemical clock is ticking backward to a time that pushes against the very earliest moments when star formation was theoretically possible. This creates what some astronomers have called the chemical enrichment problem. It is a subset of the broader early galaxy problem, and it may be even harder to solve. Building a massive galaxy quickly is one challenge. Building a chemically enriched massive galaxy quickly is another challenge entirely, because the enrichment process requires time, specifically the time for stars to live and die. You cannot speed up the nuclear reactions inside a star. You cannot make a massive star live for less than a few million years. The physics of stellar evolution sets a hard floor on the timescale for chemical enrichment, unless there is a process we have not considered. Some researchers have proposed that the first episodes of star formation in the early universe were more intense and more concentrated than anything we see in the nearby cosmos. If the first gas clouds collapsed rapidly and formed an enormous number of massive stars in a single burst, the resulting supernovae could have enriched the surrounding gas very quickly. This scenario, sometimes called a starburst, would produce a galaxy that appears chemically mature despite being chronologically young. The enrichment would happen not through a slow accumulation over many stellar generations, but through a single, violent pulse of star formation and death. There is evidence in the data to support this interpretation. The spectral properties of the dawn suggest a recent burst of intense star formation, consistent with the idea that the galaxy experienced a brief but ferocious period of stellar activity. The low gas fraction suggests that much of the original gas has already been consumed by star formation or expelled by the energy of the supernovae, and the possible galactic outflow, detected as a damped hydrogen absorber in front of the galaxy, could be the remnant of this explosive event. But even a starburst has limits. The gas has to be available in sufficient quantities for the burst to occur. The dark matter halo has to be massive enough to hold the gas together, and the cooling mechanisms that allow the gas to collapse have to be efficient enough to trigger star formation on the required timescale. Each of these requirements pushes against the predictions of the standard model. The detection of carbon in the dawn adds another dimension to the puzzle. Carbon, like oxygen, is produced inside stars and released by supernovae. But carbon and oxygen are produced in different types of stars and through different nuclear pathways. The ratio of carbon to oxygen in a galaxy can tell astronomers something about the types of stars that contributed to the enrichment. In the dawn, the carbon to oxygen ratio is consistent with enrichment primarily from core collapse supernovae, the explosions of massive stars that live fast and die young. This rules out significant contributions from lower mass stars that produce carbon through a different mechanism and take much longer to evolve. The chemical signature points squarely at massive stars, the very first stars, as the primary sources of heavy elements. The carbon to oxygen ratio is a powerful diagnostic tool because different types of stars produce these two elements in different proportions. Massive stars, those with more than roughly 8 times the mass of the Sun, produce both carbon and oxygen in their cores through a sequence of nuclear fusion reactions. When they explode as core collapse supernovae, they eject both elements into the surrounding gas. The ratio of carbon to oxygen in the ejector depends on the mass of the star and the details of the explosion. But for a population dominated by massive stars, the ratio falls within a predictable range that is distinct from the ratio produced by lower mass stars. Lower mass stars, those similar to our Sun, produce carbon through a different mechanism involving helium shell burning in their late evolutionary stages. These stars take billions of years to evolve, and they release their carbon gently through stellar winds, rather than through violent explosions. If lower mass stars had contributed significantly to the chemical enrichment of the dawn, the carbon to oxygen ratio would be shifted toward higher values. The fact that the observed ratio is consistent with pure core collapse supernova enrichment confirms that the chemical evolution of the dawn was dominated by massive short-lived stars. This is exactly what you would expect for a galaxy that is only a few 100 million years old, because only massive stars have had time to complete their entire life cycle in such a short period. This finding has profound implications. It means that the first generation of stars in the dawn must have been predominantly massive, not a mix of large and small stars like we see forming in nearby galaxies, but a population dominated by giant stars that burned hot and fast and died in spectacular explosions. This is consistent with theoretical predictions about population 3 stars, the first generation of stars formed from pristine gas. Without heavy elements to help the gas cool and fragment into small clumps, the collapsing clouds would have produced mostly large stars. the dawn may be showing us the chemical fingerprint of the very first stellar generation. But there is a tension here. If the first stars were predominantly massive, they would have been incredibly luminous. A star with 100 times the mass of the Sun shines millions of times brighter than the Sun. A population of such stars would have produced an enormous amount of ultraviolet radiation, enough to ionize the neutral hydrogen in a large volume of space around the galaxy. This process, called reionization, is one of the key events in cosmic history, and the evidence from the dawn suggests that it may have started earlier than the standard models predict. The ionizing photon escape fraction of the dawn, estimated at roughly 11%, suggests that a significant amount of ultraviolet radiation was leaking out of the galaxy and into the surrounding intergalactic medium. This escaping radiation would have begun to carve out a bubble of ionized hydrogen around the dawn, contributing to the larger process of reionization that eventually transformed the entire universe from neutral to ionized. If galaxies like the dawn were common in the early universe, and the JADES survey suggests they may have been, then the combined radiation from these early luminous galaxies could have driven reionization earlier and faster than previously thought. In May 2025, astronomers announced the detection of an even more distant galaxy, provisionally named MEMZ14, at a redshift of approximately 14.44. If confirmed, this galaxy would be even further back in time than the dawn existing when the universe was barely 280 million years old. The discovery of galaxies at these extreme distances is no longer surprising. It is becoming routine, and the more of them we find, the stronger the case becomes that the early universe was far more productive and far more complex than our models anticipated. Each new discovery pushes the boundary of what we thought was possible. Each new galaxy at the edge of the observable universe adds another data point to the growing body of evidence that the cosmos grew up faster than anyone expected, and the dawn, as the best studied and most thoroughly characterized of these extreme objects, sits at the center of this revolution in understanding. It is the benchmark against which all models of early galaxy formation will be tested. Let us now explore one of the most extraordinary alternative explanations for the dawn and objects like it. Because the standard picture of the early universe, in which ordinary stars powered by nuclear fusion were the first sources of light, may not be the only possibility. There is another theory, one that has been gathering momentum since the launch of James Webb, that proposes a fundamentally different kind of star may have existed in the earliest universe. These hypothetical objects are called dark stars. The idea of dark stars was first proposed in 2007 by physicist Catherine Fries and her colleagues. The concept is startlingly simple, yet deeply profound. In the very early universe, the first gas clouds began to collapse under gravity in regions where dark matter was especially concentrated. These regions, called dark matter halos, were the densest clumps of invisible matter in the cosmos. As the gas fell into these halos and began to compress, something unusual happened. Dark matter, whatever it is made of, is thought to consist of particles. The leading candidates are called weakly interacting massive particles. When two of these particles collide, theory predicts they can annihilate each other, converting their mass into energy. This energy takes the form of heat and radiation. In most places in the universe, dark matter particles are too spread out for annihilation to occur at a significant rate. But at the very center of a collapsing gas cloud in the early universe, where dark matter was most concentrated, the rate of annihilation could have been high enough to produce a meaningful amount of heat. This heat would have had a dramatic effect on the collapsing gas cloud. Normally, when a gas cloud collapses, it heats up and eventually ignites nuclear fusion, becoming a conventional star. But the energy from dark matter annihilation could have supported the cloud against further collapse before fusion ever began. The result would have been a star that was powered not by fusion, but by dark matter annihilation. A dark star. Dark stars would have been utterly unlike any star that exists today. Because dark matter annihilation produces energy less efficiently per unit volume than nuclear fusion, a dark star would need to be far larger than a conventional star to remain stable. Theoretical models predict that dark stars could have grown to extraordinary sizes, perhaps reaching millions of times the mass of the Sun. They would have been luminous bright enough to be visible billions of light years away, and they would have been diffused giant puffy clouds of hydrogen and helium held up by the gentle heat of dark matter annihilation at their cores. The most remarkable property of dark stars is what happens when they die. Because dark matter annihilation prevented nuclear fusion from igniting, the dark star could continue growing by accreting more gas for as long as its dark matter fuel supply lasted. When the dark matter was eventually exhausted, the star had no remaining energy source capable of supporting its enormous mass. A 2025 study showed that at masses in the range of tens of thousands to millions of solar masses, a gravitational instability causes the entire structure to collapse directly into a black hole. This is significant because it provides a natural mechanism for producing very massive seed black holes in the early universe. One of the biggest unsolved problems in astrophysics is how the supermassive black holes at the centers of galaxies grew so large so quickly. Standard models that start with small stellar mass black holes and grow them through accretion struggle to produce billion solar mass black holes in the time available. But if dark stars existed and collapsed into black holes with masses of hundreds of thousands or even millions of solar masses, those black holes would have had a huge head start. They could have served as the seeds from which supermassive black holes grew. In 2023, a team led by Cosmin Ely at Colgate University, and including Catherine Fries, identified 3 objects in the JADES survey data that were consistent with a dark star interpretation. These objects, all at extreme redshifts, had photometric properties, brightness and color that matched the theoretical predictions for supermassive dark stars. The identification was based on imaging data alone, which limited its conclusiveness. But in 2025, the same team published a follow-up study using spectroscopic data from Webb's near-infrared spectrograph. They analyzed 4 extremely distant objects, including the dawn itself and its companion, and found that all 4 were consistent with a supermassive dark star interpretation. The spectroscopic analysis revealed a particularly intriguing clue. One of the objects showed a possible absorption feature from ionized helium, a spectral signature that is predicted for supermassive dark stars, but is not expected from conventional stellar populations. If confirmed, this helium absorption feature would be a smoking gun for dark stars, a distinctive chemical fingerprint that distinguishes them from ordinary galaxies. In early 2026, the same research group published an even broader study arguing that dark stars could resolve not just 1, but 3 major puzzles from the James Webb cosmic dawn data. The 3 puzzles are the unexpectedly bright blue monster galaxies, the mysterious little red dots, compact bright objects of uncertain nature found in large numbers by Webb, and the early supermassive black holes that appear too massive for their age. The paper argues that dark stars could explain all 3 phenomena as different manifestations of the same underlying process: dark matter-fueled stellar objects that grow enormous, shine brightly, and eventually collapse into massive black holes. This is a bold claim and it remains unproven. Dark stars are still entirely hypothetical. No dark star has been definitively identified. The spectral evidence is suggestive but not conclusive, and the theory depends on specific assumptions about the nature of dark matter particles that have not been verified by laboratory experiments or direct detection efforts. The underground detectors and particle accelerators that are searching for dark matter particles have not yet found them. But the explanatory power of the dark star theory is compelling. If dark stars existed in the early universe, they would naturally explain why some objects appear too bright and too massive for their age. They would not be galaxies at all. They would be individual stars, fantastically large and fantastically luminous, that our telescopes cannot resolve into their true nature at such extreme distances. What looks like a bright early galaxy might actually be a single dark star, or a small cluster of dark stars masquerading as a galaxy in our images. This possibility has a poetic quality to it. The first lights in the universe may not have been stars in any familiar sense. They may have been something entirely new, something powered by the invisible matter that makes up a quarter of the cosmos. Dark matter, the substance we cannot see and cannot touch, and have never directly detected, may have been the engine that lit the first fires in the darkness. If dark stars are real, then the cosmic dawn was written, not in nuclear fire, but in the quiet annihilation of invisible particles. The universe found a way to make light from darkness literally. But even if dark stars explain some of the anomalies, they cannot explain all of them. The oxygen in the dawn, for instance, requires conventional stellar nucleosynthesis. Dark matter annihilation does not produce heavy elements. If the dawn contains oxygen, then real stars fusion powered stars must have lived and died within it, regardless of whether dark stars also contributed to its luminosity. The truth may involve a combination of processes, some conventional and some exotic, working together to produce the extraordinary objects that James Webb is revealing. The search for dark stars is one of the most exciting frontiers in modern astronomy. Future observations with Webb and other telescopes will aim to obtain higher resolution spectra of the most distant objects, looking for the distinctive signatures that would confirm or rule out the dark star hypothesis. If dark stars are confirmed, it would open an entirely new field of astronomy, the study of stars powered by dark matter. It would provide a new way to learn about the nature of dark matter itself, because the properties of dark stars depend directly on the properties of dark matter particles, and it would fundamentally change our understanding of how the first light appeared in the universe. Let us now zoom out and consider what all of these discoveries mean for our understanding of cosmic history. Because the story of the dawn is not just the story of one galaxy or one theoretical puzzle. It is the story of a fundamental rethinking of how the universe works. For decades, the standard model of cosmology provided a reassuringly simple and orderly picture of cosmic evolution. The universe began with the Big Bang. It expanded and cooled. The first atoms formed. Gravity slowly gathered matter into dark matter halos. Gas fell into those halos and formed the first stars. Small galaxies merged into larger ones over billions of years. And eventually, the magnificent spirals and ellipticals that we see in the nearby universe took shape through this gradual process of hierarchical assembly. The dawn has punched a hole in this picture. Not a fatal blow, not the kind of discovery that overturns the entire framework. The Big Bang is not in doubt. The expansion of the universe is not in question. Dark matter and dark energy are still the dominant components of the cosmos. but the specific details of how structure formed in the first few 100 million years after the Big Bang are now clearly wrong, or at least seriously incomplete. The models predicted a slow, cautious dawn. The universe delivered a fast, bold one. It is worth emphasizing that this is not a failure of science. This is science working exactly as it should. The models were built on the best data available at the time. The predictions were logical and mathematically consistent, but they were based on observations of the nearby universe extrapolated backward to the very beginning of cosmic history. James Webb has now given us direct observations of that very beginning. And the direct observations do not match the extrapolations. This happens in science. It is how progress is made. The models served their purpose by making testable predictions. The predictions have been tested, and now the models need to be revised. The revision process is already underway. Theorists are building new models that incorporate more efficient star formation, alternative dark matter properties, modified expansion histories, and exotic objects like dark stars. Observers are conducting follow-up studies of the dawn and other extreme early galaxies using every instrument available to characterize their properties in greater detail. And the next generation of observatories is being designed with these discoveries in mind. The Roman Space Telescope, scheduled for launch later this decade, will survey a much larger area of sky than Webb, providing the statistical census of early galaxies that is needed to determine how common objects like the dawn really are. Ground-based telescopes, like the extremely large telescope being built in Chile, will provide complementary observations at optical and infrared wavelengths with even higher angular resolution than Webb. And the Square Kilometre Array, a massive radio telescope being built in South Africa and Australia, will eventually be able to directly observe the neutral hydrogen in the early universe, mapping the process of reionization as it unfolded across cosmic time. Together, these observatories will provide a comprehensive picture of the cosmic dawn that is far more detailed and far more accurate than anything we have today. The anomalies discovered by Webb are not the end of the story. They are the beginning of a new chapter. The chapter where we finally see the first moments of cosmic history, not through models and simulations, but through direct observation of the universe as it actually was. And what we are seeing is extraordinary. The universe did not wake up slowly. It did not ease gently into existence over billions of years of gradual assembly. It erupted, it blazed, it built massive, chemically enriched, structurally complex galaxies in what amounts to a cosmic heartbeat. The dawn was not soft and tentative. It was fierce and fast and full of surprises. The dawn, that impossibly bright smudge of light sitting at the edge of the observable universe, is a messenger from this fierce beginning. It carries in its ancient photons the story of a cosmos that was more creative, more energetic, and more surprising than anyone imagined. It tells us that the universe found ways to build complex structures in a fraction of the time our models said was necessary. It tells us that the chemistry of life, the oxygen and carbon and other elements that would eventually form planets and organisms, was being manufactured far earlier than we ever thought possible. And it tells us that our understanding of the cosmos, however sophisticated and mathematically elegant, is still profoundly incomplete. There is a humility in this, a reminder that the universe is not obligated to conform to our models. We build our theories from the data we have, and we refine them as new data arrives. And sometimes the new data does not just refine the theory. It forces us to start over in certain areas, to go back to first principles and ask whether our assumptions were correct. The dawn is forcing that kind of reckoning in cosmology, not a crisis, not an overthrow, but a reckoning. A moment where the universe says, "You got the big picture right, but the details are more complicated than you thought." The details matter because the details are where the physics lives. The details of how quickly gas can collapse. The details of how efficiently stars convert that gas into light. The details of how dark matter clumps and grows in the very early universe. The details of what kinds of objects can form when the cosmos is only a few 100 million years old. These are not minor questions. They are the questions that determine the timeline and the mechanism of everything that followed, including the formation of the sun, the earth, and every living thing on it. We are all downstream from the cosmic dawn. Every atom in your body was forged in a star. Every star formed from gas that was gathered by gravity. Every gravitational structure grew from density fluctuations seeded in the first fraction of a second after the Big Bang. The chain of cause and effect that connects you to the moment of creation passes directly through the era that James Webb is now observing. And the dawn, sitting at the beginning of that chain, is telling us that the first links were forged faster and more forcefully than we ever knew. The universe is patient, but it is not slow. It is creative, but it is not gentle. And it is far stranger than any model we have yet devised. Somewhere out there, 13.4 billion light years from where you are sitting right now, a smudge of ancient light is glowing in the infrared. It was one of the first complex structures to emerge from the primordial chaos. It contains oxygen that was forged in the deaths of stars that no longer exist. It may have been illuminated by objects powered not by nuclear fusion, but by the annihilation of invisible matter. And it is forcing us to rewrite the first chapter of the greatest story ever told. This ancient smudge of light has a name now. We call it the dawn, and it has earned it, because it is showing us what the dawn of the universe actually looked like. Not the gentle, predictable sunrise we imagined, but a fast, fierce, complicated eruption of light and matter that set the stage for everything that came after. We are still reading that first chapter. We are still deciphering the message encoded in those ancient photons. But every new observation brings us closer to understanding how the universe grew up so fast and why the cosmos we inhabit today is the way it is. The mirror of the James Webb Space Telescope is pointed at the beginning, and the beginning is staring back with more questions than answers. That is not a problem. That is the whole point. The questions are the frontier, and the frontier has never been more alive. But before we accept the frontier as our final resting point, let us go deeper into the mechanics of what makes the dawn so impossible. Because the numbers, when you lay them out carefully, tell a story that is even more troubling than a casual summary suggests. Start with the mass. The dawn contains several 100 million solar masses worth of stars. A solar mass is the mass of our sun, roughly 2,000 trillion kilograms. Several 100 million of those is an almost inconceivable amount of matter gathered into a single structure. To put it in perspective, the small Magellanic Cloud, a companion galaxy visible from the southern hemisphere of Earth, has a stellar mass of roughly 300 million solar masses, and it has had 13 billion years to accumulate that mass. The dawn achieved something comparable in 300 million years, or less. But the mass alone is only part of the equation. To form that much stellar mass, you need far more gas than ends up in stars. In typical nearby galaxies, the star formation efficiency is roughly 10 to 30%. That means for every solar mass of stars formed, you need between 3 and 10 solar masses of gas in the reservoir. If the dawn has several 100 million solar masses of stars and a star formation efficiency of, say, 20%, then the total gas reservoir that fed those stars had to be in the range of 1 to 2 billion solar masses. that gas had to be gathered into the dark matter halo, cooled to the point where it could collapse and then converted and into stars, all in less than 300 million years. Now consider the dark matter halo itself. For a gas reservoir of 1 to 2 billion solar masses to accumulate the dark matter halo hosting, the galaxy had to be massive enough to gravitationally capture and hold that much gas. In the lambda CDM model, the mass of the dark matter halo scales with the mass of the galaxy it contains. For a galaxy like the Dawn, the host halo would need to have a total mass of roughly 10 to 100 billion solar masses, depending on the assumptions used. Producing a halo of that size by 290 million years after the Big Bang requires the growth of structure to have proceeded extremely rapidly in that region of the universe. In the standard model, dark matter halos grow through combinations of smooth accretion, the gradual infall of dark matter particles from the surrounding environment, and merging the collision and combination of smaller halos into larger ones. Both processes take time. The rate of growth depends on the density of the environment and the statistical properties of the initial density fluctuations. In the densest regions, halos grow faster because there is more material available for accretion and merging. But even in the densest regions, the growth rate is limited by the finite speed at which dark matter can fall into the halo. Some cosmological simulations have produced rare halos massive enough to host a galaxy like the Dawn by 290 million years after the Big Bang. But these halos are extremely rare in the simulations. They represent the most extreme statistical outliers in the dark matter distribution, the densest peaks of the densest regions. Finding one such halo in a survey might be expected. Finding several, as the JADES survey appears to have done, is harder to explain. The abundance of massive early galaxies is a statistical problem, as much as a physical one. It is not just that individual galaxies are too big, it is that there are too many of them. This statistical tension is one of the most important aspects of the early galaxy problem, and it is one of the hardest to resolve. You can imagine fine-tuning the parameters of a model to produce one extreme galaxy, but producing a whole population of extreme galaxies requires a systematic change, something that affects the entire distribution of early structures, rather than just the tail. This is why many cosmologists believe that the solution will involve a change to the underlying physics, whether in the nature of dark matter, the expansion history, or the physics of star formation, rather than a tweak to the statistical parameters. The spectral energy distribution of the Dawn provides another important constraint. A spectral energy distribution, or SED, is a plot of how much light a galaxy emits at each wavelength. By fitting the observed SED with theoretical models, astronomers can infer the galaxy's stellar mass star formation rate, dust content, and age. The SED fitting for the Dawn, using combined data from Webb and ALMA, reveals a galaxy that has been forming stars at a high rate for a significant period. The best fit models suggest a recent intense starburst layered on top of an older underlying stellar population. This implies that star formation in the Dawn was not a single sustained episode, but a complex process with variations in intensity over time. The inferred star formation rate is impressive. The models suggest the Dawn was converting gas into stars at a rate of roughly 20 to 30 solar masses per year in the period immediately before we observe it. For comparison, the Milky Way currently forms stars at a rate of about 1 to 3 solar masses per year. The Dawn was forming stars at roughly 10 times the rate of our galaxy, despite being orders of magnitude smaller and younger. This rate of star formation sustained over the galaxy's estimated lifetime is consistent with the observed stellar mass. but it also implies that the gas supply was being depleted rapidly, consistent with the low gas fraction inferred from the dynamical mass measurements. The dust content revealed by the SED is another puzzle. Dust grains are tiny solid particles made of silicates, carbon compounds, and other materials produced in stellar atmospheres and supernova explosions. Dust absorbs ultraviolet light from young stars and re-emits it at longer infrared wavelengths. The reddening of the dawn's light tells us that dust was present in this galaxy just 290 million years after the Big Bang. But dust takes time to form. It requires multiple generations of stars to produce the raw materials, specifically the heavy elements from which dust grains condense. Finding dust at this early epoch further compresses the timeline and reinforces the conclusion that star formation began very early and proceeded very quickly. Some models have attempted to explain the presence of dust through an alternative pathway. Instead of forming in stellar atmospheres and supernovae over multiple generations, dust might form rapidly in the expanding ejecta of a single generation of supernova. If the first supernova were powerful enough, and if the conditions in their expanding shells were favorable, dust grains could condense from the cooling gas within a few years of the explosion. This rapid dust formation pathway could help explain the presence of dust in the youngest galaxies without requiring multiple stellar generations. But this pathway is uncertain. Laboratory experiments and theoretical models of dust formation in supernova ejecta give mixed results. Some conditions produce abundant dust, while others produce very little. The efficiency of dust formation depends on the density, temperature, and composition of the ejecta, all of which vary from one supernova to another. Until we have better constraints on these parameters, the origin of dust in the earliest galaxies remains an open question. Let us now consider the broader population of early galaxies that provides context for the dawn. Because the dawn is the most distant confirmed galaxy, but it is far from the only surprising object that James Webb has found. In the first 2 years of operations, James Webb discovered hundreds of galaxy candidates at redshifts above 8, corresponding to the first billion years of cosmic history. Many of these have been confirmed spectroscopically. The confirmed population includes galaxies at redshifts of 10, 11, 12, 13, and now 14 each one, representing a snapshot of the universe at a different moment in its early history. By studying these galaxies as a population, astronomers can trace the evolution of structure formation across the first few 100 million years. One of the most important results from these population studies is the luminosity function, a statistical description of how many galaxies exist at each brightness level at each redshift. Before James Webb launched, the luminosity function at extreme redshifts was poorly constrained. The models predicted a specific shape with very few bright galaxies and many faint ones. James Webb has measured the luminosity function directly, and the results show a significant excess of bright galaxies compared to the models. There are more luminous galaxies at redshifts above 10 than the standard model predicted. The excess is particularly pronounced at the bright end, where the most massive and most rapidly star-forming galaxies live. This excess at the bright end is what the researchers were referring to when they said that the number density of luminous galaxies is more than 10 times higher than expected. It is a systematic discrepancy that affects the entire population, not just individual outliers, and it implies that whatever process is responsible for producing galaxies like the dawn was not rare or unusual. It was widespread, operating across many regions of the early universe simultaneously. The faint end of the luminosity function is harder to measure because the galaxies are by definition faint. Even for James Webb, detecting a typical galaxy at redshift 14 is extremely challenging. The survey coverage is limited, and the exposure times required are long. But initial results from gravitational lensing studies, which use the magnifying power of massive foreground galaxy clusters to amplify the light of more distant galaxies behind them, suggest that the faint end of the luminosity function is broadly consistent with the standard model predictions. This means the problem is primarily at the bright end. There are too many bright galaxies, not too many galaxies in total. This has important implications for the theoretical explanations. A model that increases the total number of galaxies at all brightness levels would overproduce faint galaxies, conflicting with the lensing observations. A successful model needs to preferentially enhance the bright end while leaving the faint end relatively unchanged. This is not easy to achieve. Most simple changes to the underlying physics, like increasing the overall efficiency of star formation or speeding up the growth of dark matter halos, would affect all galaxies roughly equally. Producing a selective enhancement at the bright end may require a more nuanced mechanism. One possibility is that the bright end enhancement is driven by feedback processes. In the standard model stellar feedback, the energy and radiation released by young stars regulates the rate of star formation by heating and expelling gas from the galaxy. This feedback is more effective in smaller galaxies, where the gravitational potential well is shallower. In the most massive galaxies, the potential well is deep enough that feedback has difficulty expelling the gas, allowing star formation to proceed at a higher rate. If the feedback processes in the early universe were less effective than in the nearby universe, perhaps because the gas was more pristine and cooled more efficiently, then the most massive galaxies could have formed stars at even higher rates, while smaller galaxies remained largely unaffected. This feedback-based explanation has some theoretical support. Simulations that include detailed models of stellar feedback often struggle to reproduce the observed properties of the most massive early galaxies. Reducing the effectiveness of feedback in the simulations can produce brighter, more massive galaxies without dramatically changing the properties of the faint population. But the physical justification for why feedback would be less effective in the early universe is still being debated. Another possibility involves the role of galaxy mergers. In the standard hierarchical model, the most massive galaxies are built through the merger of many smaller ones. But mergers take time, and at the extreme redshifts, where James Webb is observing, there may not have been enough time for many mergers to have occurred. If the most massive early galaxies formed not through merging, but through the rapid accretion of gas directly from the intergalactic medium, they could have built up their stellar mass more quickly than the merging model predicts. This cold flow accretion scenario, where gas streams along the filaments of the cosmic web and falls directly into the galaxy without being heated to high temperatures, could provide a fast track for galaxy growth that bypasses the slow merging process. Cold flow accretion has been seen in cosmological simulations, but its importance relative to merging at the very highest redshifts is still being quantified. If cold flow accretion dominates at redshifts above 10, it could help explain the rapid growth of galaxies like the Dawn. The gas would flow in along the dark matter filaments, settling into a disk and forming stars at a high rate. This process would be most effective in the most massive halos, where the gravitational potential is strongest, naturally producing the selective bright N enhancement that the observations require. The interplay between accretion feedback and merging in the earliest galaxies is one of the most active areas of theoretical research in post-Webb cosmology. the models are becoming increasingly sophisticated, incorporating detailed treatments of gas physics, radiative transfer chemical evolution, and dark matter dynamics. But even the most advanced simulations struggle to reproduce all the observed properties of the early galaxy populations simultaneously. This is a sign that our understanding of the relevant physics is still incomplete, and that the James Webb observations are pushing us into genuinely new territory. Now let us consider what the dawn tells us about the broader question of cosmic origins, because the technical details of star formation efficiency and dark matter halo growth, while important, are ultimately in service of a much deeper question: the question of how the universe went from nothing to everything, from the pure simplicity of the Big Bang to the staggering complexity of the cosmos we inhabit today. The Big Bang produced only the simplest possible ingredients: hydrogen, helium, a trace of lithium, and a vast amount of dark matter and dark energy whose true nature remains unknown. That is it. Everything else, every heavier element, every molecule, every dust grain, every planet, every ocean, every living thing had to be built from those simple ingredients through the action of gravity, nuclear physics, and chemistry over billions of years. Or so we thought. The dawn is telling us that the building process started earlier and moved faster than anyone predicted. Heavy elements appeared within the first few 100 million years. Dust appeared within the first few 100 million years. Massive, luminous, chemically enriched galaxies appeared within the first few 100 million years. The universe did not spend a long, quiet childhood before bursting into adolescence. It went from birth to complexity in what amounts to a cosmic instant. This acceleration of cosmic complexity has implications that extend far beyond astronomy. If the chemical ingredients for rocky planets and life were being produced in the first few 100 million years after the Big Bang, then the conditions for life could have existed much earlier in cosmic history than we previously imagined. The first rocky planets might have formed not 4.5 billion years ago like the Earth, but 10 or even 12 billion years ago, in galaxies that were already rich in the heavy elements needed for rocky planet formation. This pushes back the potential origin of life in the universe by billions of years. It raises the possibility that life, if it arises readily under the right conditions, could have appeared in the cosmos long before our sun even existed. There could be civilizations in the universe that are billions of years older than our civilizations, that arose on planets orbiting stars in galaxies that were already mature when our corner of the cosmos was still a formless cloud of gas. This is speculation, of course. We do not know how readily life arises under favorable conditions. We do not know whether the heavy elements in early galaxies were distributed in the right proportions for rocky planet formation. We do not know whether the environments in those early galaxies were stable enough to support the long-term development of life. But the James Webb observations have moved the goalposts. The question is no longer whether the conditions for life existed in the early universe. The oxygen in the dawn tells us they did. The question is what happened in those conditions. And that is a question that future generations of telescopes and missions may be able to answer. The story of the dawn is ultimately a story about the power of observation. For decades, we built models of the early universe based on the best data we had. Those models were logical, mathematically consistent, and broadly successful at explaining the universe we could see. But they were models, simplifications of a reality that is always more complex and more surprising than any model can capture. James Webb has given us the power to test those models against direct observations of the early cosmos. And the observations have revealed a universe that was more productive, more creative, and more surprising than the models predicted. This is not a crisis, it is an opportunity. an opportunity to build better models, to ask better questions, and to understand the universe more deeply than we ever have before. The dawn is a beacon from the beginning of time. It carries in its ancient photons a message that has been traveling for 13.4 billion years. The message is simple but profound. The universe grew up fast. Faster than you thought. Faster than your models said it could. And the details of how it happened are still waiting to be discovered. That message is an invitation. An invitation to keep looking, to keep asking, to keep building the instruments and developing the theories that will eventually unlock the full story of cosmic dawn. The James Webb Space Telescope has opened the door. The dawn is what we found on the other side. And the story is just beginning. We have looked back 13.4 billion years and found a galaxy that should not exist. A galaxy rich with oxygen that should not be there. A galaxy that may have been illuminated by a type of star that has never been confirmed. A galaxy that is forcing us to reconsider the fundamental timeline of everything. And yet, the universe does not owe us simplicity. It does not arrange itself for our convenience. It does not follow our models just because we spent decades building them. The universe does what the universe does. And our job, the job of science, is to observe what it does and update our understanding accordingly. The dawn has given us a lot to update. It has shown us that the first chapter of cosmic history was wilder and more complex than anyone anticipated. It has revealed that the seeds of everything, the elements, the chemistry, the structures that would eventually produce stars and planets and life were planted earlier and grew faster than the textbooks said they could. And somewhere in the darkness of the ancient cosmos, 13.4 billion light years from where you are right now, the light of the dawn is still traveling, stretched thin by the expansion of the universe, dim to a whisper of infrared, but still carrying its message, still telling its story, still waiting for a golden mirror orbiting the sun to catch it and translate it into the language of science. We caught it. We are translating it. And the translation is rewriting the first page of the story of everything. The dawn came fast. The dawn came bright. And the dawn is not finished speaking. Let us now trace the full journey of the light from the dawn, because understanding that journey helps us appreciate just how extraordinary this observation really is. Roughly 290 million years after the Big Bang, in a region of the universe that was denser and more active than average, a burst of intense star formation was underway. Massive young stars burning hot and blue were pouring ultraviolet radiation into the gas around them. The oxygen forged in the cores of earlier stars was glowing in the infrared as it was excited by the intense radiation field. Dust grains were absorbing some of the ultraviolet light and re-emitting it at longer wavelengths. The galaxy we now call the dawn was alive with activity, a tiny island of light and chemistry in the vast dark ocean of the early cosmos. The photons that left the dawn at that moment began a journey that would last 13.4 billion years. They streamed outward from the galaxy at the speed of light passing through a universe that was still mostly neutral hydrogen. Some of the photons were absorbed by the neutral gas. Others passed through, finding their way into the spaces between the still-forming structures of the cosmic web. As they traveled, the universe continued to expand, stretching the photons to longer and longer wavelengths. The ultraviolet light was stretched to visible light. The visible light was stretched to infrared. And the infrared continued to stretch as the billions of years passed. During those 13.4 billion years, the universe transformed around the traveling photons. The first galaxies merged into larger ones. The process of reionization cleared the neutral hydrogen fog, making the universe transparent to ultraviolet light for the first time since recombination. Stars formed and died by the trillions, enriching the cosmos with heavier and heavier elements. Spiral galaxies took shape, their graceful arms rotating through space. Galaxy clusters assembled, pulling together thousands of individual galaxies into gravitationally bound structures spanning millions of light years. Roughly 9.3 billion years after the photons left the dawn, a cloud of gas and dust in a spiral arm of a typical galaxy began to collapse under its own gravity. This cloud was rich in heavy elements, the legacy of billions of years of stellar evolution in the Milky Way. The cloud fragmented into smaller clumps. One of those clumps ignited nuclear fusion and became the Sun. The leftover material formed a disk of gas and dust around the young star, and from that disk, the planets of our solar system condensed. The Earth took shape roughly 4.5 billion years ago, about 9.3 billion years after the photons from the dawn began their journey. Life appeared on Earth within the first billion years. Simple microorganisms, then complex cells, then multicellular creatures. Evolution produced an astonishing diversity of life over the next 4 billion years, eventually giving rise to a species capable of curiosity mathematics and the construction of telescopes. And on December 25th, 2021, that species launched the James Webb Space Telescope into orbit around the Sun, placing it at a point 1.5 million kilometers from Earth, where it could catch the ancient photons that had been traveling since the dawn of time. When those photons finally arrived at the golden mirror of the James Webb Space Telescope, they had been traveling for more than 13 billion years. They had been stretched by a factor of 15. They carried in their wavelengths and intensities the encoded story of a galaxy that existed when the universe was barely 2% of its current age. The telescope's instruments collected these photons, measured their wavelengths, and translated the data into the spectra and images that scientists on Earth would spend months analyzing. The chain of events connecting the emission of those photons to their detection is almost unfathomably long. It spans the entire history of the universe. It encompasses the formation of galaxies, the creation of heavy elements, the birth of stars and planets, the emergence of life, the evolution of intelligence, and the development of technology capable of building a space telescope. And yet, each link in that chain is connected to every other. The oxygen in the dawn was forged in the same nuclear processes that forged the oxygen in your lungs. The gravity that pulled the gas together to form the dawn is the same gravity that holds you to the surface of the Earth. The same physics that lit the first stars billions of years ago is still burning in the sun that warms your face today. This continuity is one of the most profound aspects of the story. The dawn is not a curiosity from a distant past that has no relevance to the present. It is part of the same cosmic process that produced us. Understanding how the dawn formed is part of understanding how we came to exist. The elements in your body were manufactured in stars that were themselves made possible by the processes that began in galaxies like the dawn. You are made of star stuff, as the famous saying goes. But the dawn shows us that the factories producing that star stuff were up and running much earlier than we thought. Let us now examine some of the specific scientific puzzles that remain open and that future observations may resolve. Because while the dawn has raised many troubling questions, each question also points toward a potential answer that would deepen our understanding of the universe. The first open question concerns the initial mass function of the first stars. The initial mass function describes the distribution of stellar masses in a population. In nearby galaxies, the initial mass function follows a predictable pattern with many more small stars than large ones. the Sun at one solar mass is fairly typical. Most stars are smaller and dimmer, and only a small fraction are much larger and brighter. But in the very early universe, where the gas was pristine and the cooling mechanisms were different, the initial mass function may have been very different. Some theories predict that the first stars were predominantly massive, perhaps hundreds of times the mass of the Sun. Others predict a mix of masses more similar to what we see today. The chemistry of the dawn provides indirect evidence about the initial mass function of its first stars. The carbon to oxygen ratio, the overall metallicity, and the absence of certain spectral features all carry information about the types of stars that contributed to the chemical enrichment. As the spectral data improves with future observations, astronomers will be able to constrain the initial mass function more tightly and determine whether the first stars were indeed as massive as theory predicts. The second open question concerns the topology of reionization. Reionization did not happen uniformly across the universe. It started in small bubbles around the first galaxies, and then those bubbles grew and merged until the entire universe was ionized. The size and distribution of these bubbles at different times during the reionization epoch tells us about the abundance and luminosity of the sources that drove the process. The dawn, with its significant escape fraction of ionizing photons, would have been surrounded by a bubble of ionized hydrogen that grew as the galaxy continued to produce ultraviolet radiation. Mapping these bubbles is one of the key goals of current and future observations. The detection of a damped hydrogen absorber in front of the dawn provides a direct measurement of the neutral hydrogen column density along the line of sight. This measurement constrains the local ionization state of the intergalactic medium at the galaxy's redshift. By combining similar measurements from many galaxies at different redshifts, astronomers can build a statistical picture of how reionization progressed across the first billion years of cosmic history. The third open question concerns the nature of the dark matter halo, hosting the dawn. The dynamical mass inferred from the gas motions within the galaxy provides a rough estimate of the total mass, including dark matter. But the uncertainties are large, and the measurement provides only a single number, rather than a detailed picture of the halo structure. Future observations with higher spectral resolution could map the velocity field of the gas within the dawn in greater detail, providing constraints on the dark matter distribution within the halo. This would help determine whether the halo is consistent with standard cold dark matter predictions, or whether modifications to the dark matter model are needed. The fourth open question is whether the dawn had any precursor structures. The chemical enrichment and dust content suggest that star formation began at least 100 million years before we observed the galaxy. This means there must have been an earlier phase of activity that we are not directly seeing. Were there smaller protogalactic fragments that merged to form the dawn? Were there isolated pockets of star formation scattered across the region that eventually coalesced into a single structure? Or did the dawn form in a single massive collapse event, with all the star formation happening in one concentrated burst? Each scenario makes different predictions about the morphology and kinematics of the galaxy predictions that could potentially be tested with higher resolution imaging and spectroscopy. The fifth open question concerns the fate of the dawn. We are seeing this galaxy at one specific moment in its history, 290 million years after the Big Bang. But the galaxy continued to evolve for the next 13.5 billion years. It merged with other galaxies. It formed new generations of stars from the enriched gas in its environment. It may have grown a supermassive black hole at its center. By the present day, the dawn has been transformed beyond recognition. It is no longer a separate galaxy. It has been absorbed into a larger structure, perhaps a massive elliptical galaxy, or a component of a galaxy cluster. Identifying the descendant of the dawn in the present-day universe is a fascinating challenge that combines observations of the distant past with simulations of cosmic evolution. Some cosmological simulations have attempted to trace the evolution of extreme early galaxies forward in time to predict what they would look like today. The results suggest that galaxies like the dawn are likely the progenitors of the most massive galaxies in the present-day universe, the giant ellipticals that sit at the centers of galaxy clusters. These behemoths, containing trillions of stars, may have had their origins in the rapid early growth episodes revealed by James Webb. The dawn may be the embryonic form of a galaxy that is now one of the largest structures in the cosmos. Let us now return to the dark star hypothesis and explore it more thoroughly, because it represents one of the most radical possible solutions to the puzzles raised by the dawn. The central idea behind dark stars is that the very first luminous objects in the universe were not powered by nuclear fusion at all. Instead, they were powered by the energy released when dark matter particles collided and annihilated each other. This energy, in the form of heat and radiation, kept the collapsing gas cloud from igniting fusion and allowed the object to grow to enormous sizes while remaining relatively cool compared to a conventional star. The key distinction between a dark star and a conventional star is the energy source. A conventional star derives its luminosity from nuclear fusion, the process of fusing light atomic nuclei into heavier ones and releasing the binding energy. This process is extremely efficient per unit mass of fuel, which is why stars can be relatively compact. A dark star derives its luminosity from dark matter annihilation, which is much less efficient per unit volume. To produce the same total luminosity as a conventional star, a dark star has to be much larger because the dark matter annihilation occurs throughout a large volume of the stellar interior, rather than being concentrated in a compact core. Theoretical models predict that dark stars could have reached sizes comparable to the radius of our entire solar system. A dark star with 1 million solar masses might have a radius of roughly 10 astronomical units, about the distance from the Sun to Saturn. Despite this enormous size, the surface temperature of the dark star would be relatively low, perhaps 1000 to 5000 Kelvin, giving it a yellowish or whitish appearance. The combination of large size and moderate temperature would make the dark star extremely luminous, potentially shining with 1 billion times the luminosity of the Sun. At the distances and redshifts where James Webb is observing, a single supermassive dark star would be too small to resolve as an extended object. It would appear as a point source or a very compact source in the images. This is one of the reasons the dark star hypothesis is hard to test. A dark star and a small compact galaxy would look very similar in the low-resolution images available at these extreme distances. Only detailed spectroscopy, specifically the identification of unique spectral features like the helium absorption signature, can distinguish between the two interpretations. The 2025 study by Ilir Mahmoud Polin and Fries examined 4 of the most distant objects in the JADES survey and found that all 4 were consistent with a dark star interpretation based on both their spectra and their morphology. 2 of the 4 objects, including the dawn, are slightly extended in the images, suggesting they are not point sources, but the researchers showed that even these extended sources could be explained as dark stars surrounded by a nebula of ionized gas that the dark star's radiation has illuminated. The nebula would appear as a diffuse glow around the point, like dark star, making it look like a small galaxy in the images. One of the most intriguing aspects of the dark star scenario is what happens after the dark matter fuel runs out. Without the energy from dark matter annihilation, the enormous gas cloud can no longer support itself against gravity. The collapse is catastrophic and complete. The entire mass of the dark star falls inward and forms a black hole. The mass of this black hole would be comparable to the mass of the dark star, potentially millions of solar masses. This is far more massive than any black hole that could form from the collapse of a conventional star, which typically produces black holes of only a few to a few hundred solar masses. These massive black hole remnants would then become the seeds for the supermassive black holes that we observe at the centers of galaxies. In the Standard Model building, a supermassive black hole from a small stellar mass seed requires billions of years of slow accretion. But if the seed was already millions of solar masses, thanks to the collapse of a dark star, the growth to a billion solar mass supermassive black hole becomes much easier and can happen much faster. This is why the dark star hypothesis is so attractive to cosmologists. It potentially solves two problems at once: the problem of unexpectedly bright early objects and the problem of unexpectedly massive early black holes. The dark star hypothesis also offers a potential explanation for the mysterious little red dots that James Webb has discovered in large numbers. These compact red objects have been found at a wide range of redshifts, and their nature is still debated. Some appear to be compact galaxies with significant dust reddening. Others show spectral signatures consistent with active galactic nuclei. The dark star theory suggests that some little red dots might be dark stars in a transitional phase, objects that are running out of dark matter fuel and beginning to contract and heat up before their final collapse into a black hole. In this phase, the dark star would become redder and more compact, potentially matching the observed properties of the little red dots. If this interpretation is correct, then the little red dots are not just another class of peculiar early galaxies. They are the death throes of the dark stars, the brief visible phase between a dark matter-powered existence and a dark collapse into a black hole. The universe would be littered with these transient objects during the cosmic dawn era, each one marking the end of a dark star and the beginning of a supermassive black hole seed. It is a dramatic and beautiful picture, if speculative. The confirmation or rejection of the dark star hypothesis will require several lines of evidence. First, higher quality spectra of the candidate dark stars are needed to search for the distinctive helium absorption features that the theory predicts. James Webb has the capability to obtain these spectra, but it requires very long exposure times on individual objects. Second, resolved imaging at the highest possible angular resolution is needed to determine whether the candidates are truly point sources or extended objects. The more compact the source, the more likely it is to be a single object, like a dark star, rather than a collection of stars in a galaxy. Third, theoretical models of dark stars need to be refined to make more specific and testable predictions about the spectral signatures, variability, and spatial properties of these objects. And fourth, progress in dark matter detection experiments is needed to determine the properties of dark matter particles, because the dark star theory depends on specific assumptions about how dark matter particles interact and annihilate. The coming decade will be decisive for the dark star hypothesis. Webb will continue to observe the earliest objects in the universe with increasing depth and spectral resolution. Ground-based telescopes like the Extremely Large Telescope will provide complementary observations at shorter wavelengths, and laboratory experiments will continue to search for dark matter particles If dark stars exist, we are likely to know within the next 10 to 20 years. And if they do, it will be one of the most profound discoveries in the history of physics, confirming that dark matter is not just a gravitational scaffold, but an active source of energy that powered the first lights in the cosmos. Let us close by returning to the dawn itself and considering what this single smudge of ancient light means for our place in the universe. The dawn is a galaxy that existed 290 million years after the Big Bang. It is 1,600 light-years across. It contains hundreds of millions of solar masses of stars. It is rich in oxygen and carbon elements that were forged in the cores of stars that had already lived and died before the galaxy reached the state we observe. It is bright, mature, and complex, far more so than any model predicted for a galaxy at this distance. It is either a conventional galaxy that grew up impossibly fast, or it is something we have never seen before, a dark star or a cluster of dark stars masquerading as a galaxy in our images. And it is currently the most distant confirmed galaxy in the observable universe. The light we detect from the dawn has been traveling for 13.4 billion years. By the time it reached the gold-coated mirror of the James Webb Space Telescope, it had been stretched by a factor of 15, dimmed to a whisper of infrared, and smeared across 13.4 billion years of cosmic history. And yet it still carried enough information for us to determine the galaxy's distance, its mass, its chemical composition, its star formation rate, and its physical size. The fact that we can extract this much information from photons that have been traveling since before the Earth existed is one of the most extraordinary achievements of human civilization. But the most extraordinary thing about the dawn is not what it tells us about the past. It is what it tells us about the future of our understanding. Every time humanity has built a new tool to observe the universe, we have found things we did not expect. The telescope revealed that the Earth is not the center of the cosmos. Spectroscopy revealed that stars are made of the same elements as rocks and oceans. Radio astronomy revealed the cosmic microwave background. Space telescopes revealed dark energy. And now James Webb is revealing that the very first chapter of cosmic history was more dramatic, more complex, and more mysterious than we ever imagined. Each of these discoveries humbled us. Each one forced us to revise our understanding and acknowledge that the universe is bigger, stranger, and more wonderful than we thought. The dawn is the latest in this long line of humbling revelations. It is a reminder that the cosmos is not obligated to be simple. It is not obligated to match our models. It is not obligated to grow up slowly just because our equations say it should. The universe does what it does, and our greatest privilege as a species is to watch it do it and try to understand. The dawn is still there, still glowing in the infrared, still sending its ancient light across the expanding void. Now the galaxy itself has been transformed beyond recognition, absorbed into larger structures over 13 billion years of cosmic evolution. But the light it emitted 290 million years after the Big Bang is still traveling, still carrying its message, still waiting to be caught by a mirror and translated into understanding. We caught some of those photons in 2024. We measured them, we analyzed them, and what they told us is this. The universe grew up fast. The first chapter was not a quiet prelude. It was a burst of creativity and complexity that set the stage for everything that followed. The oxygen in the dawn is the ancestor of the oxygen in your blood. The stars that died to produce it are the ancestors of the stars that would eventually form our sun. The gravity that held it together is the same gravity that holds you to the ground. We are connected to the dawn by an unbroken chain of physics and chemistry that stretches back 13.4 billion years. And by looking at this ancient galaxy, we are looking at ourselves, at the process that made us, at the cosmic machinery that turns hydrogen into humans. The dawn came fast, it came bright, and it came with more questions than answers. That is exactly how it should be. The golden mirror is still watching, the universe is still speaking, and the most distant confirmed galaxy in the cosmos is still teaching us that the greatest discoveries come not from confirming what we already know, but from confronting what we do not. The dawn, a tiny smudge of light, a ghost from the beginning of time, and a challenge that will keep scientists busy for generations. The story of the universe just got a new first chapter, and it is far more interesting than the one we wrote before. There is one more aspect of the dawn that deserves careful attention before we close. It concerns the nature of the light itself and what the specific wavelength measurements reveal about the conditions inside this ancient galaxy. When astronomers analyzed the mid-infrared detection of the dawn using Webb's MIRI instrument, they found that the brightness at 7.7 micrometers was higher than what you would predict by simply extrapolating from the shorter wavelength measurements. This excess brightness at longer wavelengths indicates the presence of strong emission lines from ionized gas within the galaxy. Specifically, the excess is consistent with bright emission lines from hydrogen and oxygen, the same elements detected through other means. The presence of these strong emission lines tells us something important about the physical conditions inside the dawn. Emission lines are produced when atoms are excited by energetic radiation and then release that energy as photons at specific wavelengths. The strength of the lines depends on the intensity of the radiation field, the density of the gas, and its chemical composition. Strong oxygen emission lines indicate that the gas is being illuminated by intense ultraviolet radiation from very hot stars, and that the oxygen abundance is significant enough to produce a detectable signal at the extreme distance of 13.4 billion light-years. The ionization state of the gas provides additional clues. The oxygen detected by ALMA was doubly ionized oxygen, meaning each oxygen atom had lost 2 of its electrons. Producing doubly ionized oxygen requires photons with energies above a certain threshold, which in turn requires very hot stars with surface temperatures exceeding about 35,000 degrees. This confirms that the stellar population in the dawn included massive luminous stars that were producing copious amounts of hard ultraviolet radiation. These are exactly the types of stars that would have been needed to drive reionization in the surrounding intergalactic medium. The spatial distribution of the oxygen emission is also informative. The ALMA observations detected the oxygen line at a single position, consistent with the center of the galaxy as seen by Webb. The emission appears to be compact, concentrated in the central region of the galaxy, rather than spread uniformly across its full extent. This could indicate that the star formation, and therefore the oxygen production, is concentrated in the core of the galaxy, with the outer regions being more pristine and less enriched. Alternatively, it could reflect the limited spatial resolution of the ALMA observations at this extreme distance. Higher resolution observations in the future could distinguish between these possibilities. The velocity width of the oxygen line provides a measurement of the internal motions of the gas within the dawn. Gas that is moving toward us appears slightly blue shifted, while gas moving away appears slightly red shifted, broadening the emission line. The measured line width corresponds to a velocity dispersion that, combined with the physical size of the galaxy, yields a dynamical mass estimate. This dynamical mass, roughly 1 billion solar masses, includes contributions from stars, gas, dark matter, and anything else within the measurement region. The fact that the dynamical mass is only modestly larger than the stellar mass suggests that the gas fraction is low, consistent with the interpretation that most of the available gas has already been converted into stars or expelled from the galaxy. This low gas fraction is remarkable for such a young galaxy. In the standard picture, galaxies at this early epoch should still be gas-rich, actively accreting fresh material from the intergalactic medium and converting it into stars. A galaxy that has already depleted its gas reservoir implies either extremely efficient star formation that consumed the gas, or powerful outflows that ejected the gas, or both. Either way, the dawn has already gone through an eventful and dramatic phase of evolution that would normally take billions of years to complete. The possibility of galactic outflows is particularly intriguing. If the intense star formation in the dawn produced a large number of supernovae in a short period, the combined energy of those explosions could have driven a powerful wind that swept gas out of the galaxy. This wind would carve channels through the interstellar medium, allowing ultraviolet radiation from the remaining stars to escape more easily into the surrounding space. The high ionizing photon escape fraction estimated for the dawn is consistent with this picture. The outflow clears the gas, the radiation escapes, and the galaxy simultaneously depletes its fuel supply and contributes to the reionization of the surrounding universe. This outflow scenario has been modeled in detail by theoretical groups. One influential model developed by Andrea Ferrara and colleagues predicts that the dawn experienced a recent starburst phase, followed by radiation-driven outflows that cleared the galaxy of dust and gas. In this model, the galaxy went through a brief period of maximum productivity, forming a large fraction of its total stellar mass in a single intense burst, and then the feedback from that burst shut down further star formation by removing the fuel. The galaxy we observe is in the immediate aftermath of this burst, still bright from the recent star formation, but already depleting and shedding its gas. If this model is correct, it has implications for how we should interpret the early galaxy population more broadly. Perhaps many of the bright early galaxies that James Webb is detecting are caught in a similar post-starburst phase, briefly visible at maximum brightness before fading as their gas supply runs out. This would help explain why they appear so common in surveys. They are not representative of the average early galaxy. They are the ones caught at the peak of a brief bright episode, visible precisely because they are in this transient phase. The average early galaxy might be much fainter and more typical, simply hidden below the detection threshold. This idea is sometimes called the bursty star formation hypothesis, and it has gained significant traction in the post-Webb theoretical community. In this picture, early galaxies do not form stars at a steady rate. Instead, they go through cycles of intense bursts, followed by quiet phases. During the burst phase, the galaxy is bright and would be detected by Webb. During the quiet phase, it is faint and would be missed. If the burst phase is short compared to the quiet phase, then the observed population of bright galaxies overrepresents the bursty tail of the distribution. The average galaxy would be much less impressive than the ones we see. This hypothesis is testable. If early galaxies go through bursty cycles, then the scatter in their properties at a given redshift should be large. Some should be bright, some faint, some chemically enriched, some pristine. The variety should be much greater than in a model where all galaxies evolve smoothly and steadily. And indeed, the growing sample of early galaxies from James Webb shows enormous diversity. Some are bright and massive like the dawn. Others are faint and compact like its companion. Some show strong emission lines indicating active star formation. Others show weak or absent lines, suggesting a recent decline in activity. This diversity is consistent with the bursty star formation picture, and it is one of the strongest arguments in its favor. But the bursty star formation hypothesis does not fully resolve the tension with the standard model. Even if the bright galaxies are caught at the peak of a burst, the total stellar mass assembled during the burst still needs to have formed from gas that was available in the dark matter halo. And the dark matter halo still needs to be massive enough to have accumulated that gas in the available time. The burstiness helps explain why the galaxies are bright, but it does not eliminate the need for rapid structure formation. The underlying timing problem remains. Let us also consider what the dawn and its fellow early galaxies tell us about a concept known as the mass gap. In the standard model, there is a well-defined relationship between the mass of a dark matter halo and the mass of the galaxy it contains. This relationship, calibrated against observations of nearby galaxies, predicts how much stellar mass should exist in halos of a given size at a given epoch. At the earliest times, the most massive halos are predicted to be relatively modest, and the stellar mass they contain should be correspondingly small. The dawn and other massive early galaxies violate this relationship. They contain more stellar mass than expected for halos of the size that should exist at their redshift. This means either the halos are more massive than predicted, or the star formation efficiency is higher than calibrated, or both. The mass gap between the predicted and observed stellar masses at the earliest times is one of the most robust features of the early galaxy problem. It persists across different surveys, different analysis methods, and different assumptions about stellar populations and dust. Closing the mass gap will require a combination of observational and theoretical advances. On the observational side, more precise measurements of stellar masses, halo masses, gas masses, and star formation rates in early galaxies will tighten the constraints on the physical models. On the theoretical side, simulations that incorporate the full complexity of baryonic physics, including gas, accretion, cooling star formation feedback, and chemical enrichment, will need to be refined and tested against the growing body of James Webb data. The interplay between observation and theory is the engine of progress in cosmology. James Webb provides the observations. Theorists build models to explain them. The models make predictions that can be tested with new observations. And the cycle continues with each iteration, bringing us closer to a complete understanding of how the universe evolved from simplicity to complexity. The dawn is a key data point in this cycle, a benchmark that any successful model of early galaxy formation will need to reproduce. We are living in one of the most exciting periods in the history of astronomy. The James Webb Space Telescope has opened a window onto the first few 100 million years of cosmic history, revealing a universe that is more dynamic, more productive, and more mysterious than anyone expected. The dawn sits at the center of this revolution, the most distant confirmed galaxy in the observable universe, a tiny smudge of light that carries the weight of cosmological significance. The questions it raises are profound. How did the universe build massive galaxies so quickly after the Big Bang? What mechanisms allowed heavy elements to accumulate in just a few 100 million years? Were the first stars conventional fusion-powered giants, or exotic dark matter-powered behemoths? Is the standard model of cosmology fundamentally correct, or does it need significant revision? These are not abstract academic questions. They are questions about the origin and nature of the cosmos that produced us. They are questions about the chain of events that led from the Big Bang to the formation of the Sun, the Earth, and everything on it, including you. The dawn is not just a galaxy. It is a challenge to our models, our assumptions, and our understanding of the universe. It is a ghost from the very beginning of time that refuses to be explained away. And in its refusal, it is pushing us toward a deeper and more complete understanding of how the cosmos works. The golden mirror of the James Webb Space Telescope is still collecting photons from the edge of the observable universe. The next discovery could be even more distant, even more troubling, even more transformative. The dawn may hold the distance record today, but the universe is vast, and our exploration of it has barely begun. Somewhere out there, even older and even more impossible galaxies may be waiting to be found. And when we find them, we will ask the same question that the dawn has already forced us to ask. How did the universe grow up so fast? The answer, when it comes, will change everything we think we know about the cosmos. And it will come from the same place all great answers come from a willingness to look at the evidence, however troubling, and follow it wherever it leads. The light of the dawn is ancient, but the questions it raises have never been more urgent, and the adventure of answering them has never been more alive. Before we truly close, there is one more thread worth pulling. It concerns the engineering marvel that made this discovery possible, and the human story behind the machine that caught the dawn. The James Webb Space Telescope was not an easy thing to build. The project began in the late 1990s as the successor to the Hubble Space Telescope. At the time, the estimated cost was roughly $1 billion, and the launch was planned for 2007. But as the design evolved and the scientific ambitions expanded, the project grew more complex and more expensive. The primary mirror had to be segmented into 18 pieces so it could fold to fit inside the rocket fairing and then unfold in space with nanometer precision. The sun shield, a 5-layer structure the size of a tennis court, had to deploy flawlessly in the vacuum of space to keep the telescope cold enough for its infrared instruments to function. There were 344 single-point failure mechanisms in the deployment sequence, any one of which could have ended the mission. The cost eventually reached roughly $10 billion. The launch was delayed again and again as engineers struggled with the unprecedented technical challenges. The project came close to cancellation more than once, saved each time by the scientific community's insistence that the science it would deliver was worth the investment. And on Christmas Day 2021, the Ariane 5 rocket carrying Webb lifted off from the European spaceport in French Guiana and began the journey to its final destination. The deployment sequence that followed was one of the most nerve-wracking episodes in the history of space exploration. Over the course of 2 weeks, the sun shield unfolded layer by layer the secondary mirror deployed on its support struts, and the 18 primary mirror segments swung into position. Each step had to work perfectly. There was no possibility of repair. Unlike Hubble, which orbits close to Earth and was famously repaired by astronauts after its mirror was found to have a flaw, Webb orbits 1.5 million kilometers from Earth, far beyond the reach of any crewed spacecraft. If anything went wrong during deployment, the mission was over. Nothing went wrong. The deployment was flawless. The mirror alignment achieved over the following months using tiny actuators behind each mirror segment produced images of stunning sharpness. When the first images were released to the public in July 2022, the reaction was overwhelming. Hundreds of millions of people around the world saw the deep field image showing thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. The beauty of the images captured the public imagination in a way that few scientific projects ever have. But behind the beauty was the science, and the science has been transformative. In less than 3 years of operations, James Webb has rewritten our understanding of the early universe, revealed the atmospheric composition of exoplanets, discovered organic molecules in the disks around young stars, and captured detailed images of objects within our own solar system. The telescope has exceeded expectations in virtually every area of its scientific portfolio. The discovery of the dawn is arguably the most significant individual result from the mission so far. It has been described by some astronomers as the most important extragalactic discovery with James Webb to date. Its implications touch on fundamental questions about the nature of dark matter, the physics of star formation, the timeline of cosmic evolution, and the origin of the chemical elements. It is the kind of discovery that defines a generation of astronomy. And it almost did not happen. The initial identification of the dawn was complicated by its proximity to a foreground galaxy in the sky. The two objects appeared close together in the images, and it was not immediately clear whether they were at the same distance or separated by billions of light years. It took additional deep imaging with specially designed filters to build confidence that the dawn was genuinely at extreme distance. And it took a 75-hour spectroscopic campaign, one of the longest individual observations in the history of the JADES program, to confirm the redshift and cement the discovery. The team that made the discovery was international drawing from institutions across the United States, Europe, and beyond. Stefano Carniani of the Scuola Normale Superiore in Italy led the initial spectroscopic analysis. Brant Robertson of the University of California, Santa Cruz co-leads the JADES program and led the statistical analysis of what the discovery implies for the broader galaxy population. Kevin Hainline and Jake Helton of the University of Arizona contributed critical analyses of the imaging and mid-infrared data. The ALMA observations that detected oxygen were led independently by two teams, one led by Carniani and another by Sander Schoos of Leiden Observatory in the Netherlands. The convergence of their independent results provided strong confidence in the detection. The collaborative nature of this discovery is itself noteworthy. No single institution, no single instrument, and no single team could have made this discovery alone. It required the combined capabilities of James Webb and ALMA. It required the combined expertise of observers, theorists, instrument scientists, and data analysts from dozens of institutions. And it required years of careful planning, from the design of the JADES survey strategy, to the selection of spectroscopic targets, to the painstaking analysis of the resulting data. This is how modern astronomy works. The biggest discoveries are not made by lone geniuses working in isolation. They are made by large, diverse international teams, leveraging the capabilities of the most powerful instruments ever constructed. The story of the dawn is as much a story of human collaboration as it is a story of cosmic physics. It took thousands of people, decades of effort, billions of dollars, and the combined intellectual resources of the global scientific community to catch those ancient photons and translate them into understanding. And the work is far from finished. The dawn has been observed. Its distance has been measured. Its chemical composition has been characterized, but the full implications of the discovery are still being digested. Theorists are building new models. Observers are planning follow-up observations, and the broader community is debating what changes to the standard cosmological framework are necessary to accommodate this and other early galaxy discoveries. The next few years will be critical. Webb will continue to observe the early universe with increasing depth and precision. New galaxies at extreme redshifts will be discovered and characterized. The statistics of the early galaxy population will improve, providing tighter constraints on the models. and the theoretical framework will evolve, incorporating new physics where the old physics falls short. The universe has given us a gift in the dawn, a window into the very first moments of cosmic structure formation, a laboratory for testing our most fundamental theories about gravity, dark matter, and the physics of star formation, and a reminder that the cosmos is always more surprising than we expect. We are the universe looking back at itself. When we observe the dawn, we are looking at the beginning of the process that eventually produced the eyes and minds doing the looking. The oxygen in that ancient galaxy and the oxygen in your bloodstream were manufactured by the same nuclear processes, separated by 13 billion years, but connected by an unbroken chain of physics. That connection is what makes the dawn not just a scientific discovery, but a human one. It is a discovery about where we come from, about the cosmic machinery that turns simple elements into complex worlds, about the chain of events that had to happen in that specific order, at that specific pace for you to exist. The dawn of the universe came fast, and it left behind a message written in oxygen and starlight. We are only now learning to read it. And every photon we catch from that distant epoch brings us one step closer to understanding not just where the universe came from, but where we came from with it. The James Webb Space Telescope is our translator, the dawn is our text, and the reading has only just begun.